In this section, we're going to take a look at systems of linear equations in two variables. And so the objective of this section is to make sure that we define what a linear system in two variables might be and what the solutions might look like. Be able to solve by three methods: graphing, substitution, and elimination, to determine if a system is dependent or independent, and then also to determine if the system is consistent or inconsistent. And then finally, we're going to solve applied problems that are going to be using these systems of equations in two variables. So a system in general is going to be two or more equations that have some relationship. And so a system of linear equations in two variables and also consists of two linear equations if they have some relationship. So for instance, notice there's no squares. There's only two variables. Notice there's no square roots. Notice there's no trigonometry going on in here. And so this would be a system of equations in two variables, right? The solution to an ordered pair is going to be an ordered pair to a system, and it satisfies both of these systems or both of these equations, simultaneously. So what we could do is we could just graph both of these on the same plane, and the point of intersection should give us what the solution is going to be. So if we have a graphing device, being able to determine what the solution is should be pretty easy, because all we have to do is just graph both of these equations, right? Now, first thing we want to do is, if I give you a solution, we want to make sure that a solution is viable or not. Okay, so let's say we give the solution -2, -4, okay, and we want to determine if that really is a solution to this system. So what I'm going to do is I'm just going to substitute -2 for x, and I'm going to substitute -4 for y back into both equations, okay? So in equation 1, if I substitute, I get 2 times -2 minus 3 times -4 equals 8. Okay, and we're not sure if that's true or not, right? But if we go equals positive 8, excuse me. And if we compute, this gives us -4 plus 12 equals 8, which is a viable statement, all right? But that doesn't mean it's a solution, because we still have to check equation 2, all right? So if we substitute back into equation 2, we're going to get -2 minus 2 times -4 equals 6. And that would yield -2 plus 8 equals 6, and that's a viable statement as well. And so the answer would be yes, okay? And it's going to be a solution, since -2, -4 satisfies both equations, okay? If either of them are not satisfied by the ordered pair, then it would not be a solution. Now, let's say for some reason we're solving the system and y equals -4 is obtained. We want to try to find the solution set for this. So all we're going to do is we're going to substitute -4 back into either of these. I always try to pick the one that's a little bit easier. Okay, in this case, it looks like that this one's just going to be a little bit easier, the second one, just because there's no coefficient for the y. All right, we could plug it into the first because it does satisfy both, but I'm just going to plug it into the easier one. So we get -4 is going to be equal to 4x minus 6. And then from there, we just solve it like a regular linear equation. So what I'm going to do is add 6 to both sides, and we get 2 equals 4x. And then I'm going to divide both sides by 4. And so 1/2 would be equal to x. If we want to make sure that this is true, what we might want to do is just substitute 1/2 and -4 back into the original, into the first equation, okay? And I'm just going to do it because it's one of the first times that we're dealing with systems. So I get 4 times 1/2 minus 2 times -4 equals 10. And we know 1/2 of 4 is 2. -2 times -4 is 8. And that's a viable statement, okay? So this is going to be our solution. And so the solution set would be 1/2 comma -4, okay? And we might say that x is equal to the set, since it is truly asking for a solution set, all right? This would probably be the answer that we probably want to give. So, as we mentioned before, there's three methods for being able to solve systems: graphing, substitution, and elimination, right? We already noted that if we want to solve a system by using the graphing method, we're going to graph both lines on the same coordinate axis. The point of intersection, if it exists, is going to be the solution to the system. Okay, so just like we had up here, we had this system, we graph both of these, okay, and then this is the point that we try to intersect at, and then so x is 4, y is -1. The problem with graphing is that if we graph by hand, or even sometimes with a calculator, we don't always get an exact answer, and also if we graph by hand, there's an accuracy issue. But it is a way for us to at least get some sort of proximal um, solution. In other words, we can kind of get an estimate. So let me just show you by using Desmos how we can go ahead and solve these systems by graphing. In your calculator, what you would have to do is you would have to solve both of these equations for y. Okay, so you'd have to rewrite the system as y equals 2 minus x and -y equals 4 minus x, or this equation, if we multiply by -1 by changing all the signs, would look like this. Okay, so y equals -4 plus x. So this is what you would have to do in your calculator, but in Desmos, it's really nice and easy. Okay, so I'm just going to go ahead and graph this. So we have x plus y equals 2 as one equation, and the other equation was x minus y equals 4. Right, so we have x minus y equals 4, right? And we can clearly see that the solution is 3, -1, right? So there is one solution, and the solution is going to be 3, -1 by graphing. Now, not every system is going to have a solution, okay? And we're going to define these terms in a few moments as well. So again, what we would have to do is we would have to solve both of these equations, okay, to put them into our calculator. So I would subtract 4x, okay? So for this first equation, I would get -2y equals 1 minus 4x, and I would divide by -2, and so y would be equal to -1/2 plus 2x. That's what I would plug into my calculator. And then for this one, I would just go through and add 2x. So y would be equal to 4 plus 2x. So again, in our calculators, this is what we would have to do. In Desmos, we could just go ahead and plug it in immediately. Okay. So in our calculator, we have 4x minus 2y equals 1. And then the other equation is going to be -2x plus y equals 4. Oh, sorry, skip down. So -2x plus y equals 4. Now, I want you to notice that even if we zoom out, what we notice is that these two lines are parallel and they never intersect. Okay, so lines are parallel. And so what that means is that they never intersect, which means that there is no solution to this system. Now, finally, not every, now we've seen one that has one solution, okay, which it intersects. We've seen ones that have no solution. Let's take a look at this last one. Okay, so we have 1/2 x plus 2y equals 5, x plus 4y equals 10. We could solve this for x and y, but I'm just going to plug it in the interest of time. So we have 1/2 x plus 2y equals 5. Okay, and then we have x plus 4y equals 10. All right, now check it out. Before I punch in the last value 10, notice that this is a line. Okay, it passes through the point 0, 10, and if I zoom in a little bit, we have another point that it passes through. It looks like 0, 3, and 10, 0. Now, if I plug in 10, right, notice that we have the exact same line. Okay, so in this line, okay, And notice if I just move it down by plugging 9 instead, if I plug in 10, this line overlaps, okay? What that means is that there's an infinite number of solutions, okay? Okay. And that's because the two lines actually are the same line if we were to algebraically manipulate them. Okay. So notice in this one, if I was to multiply this by a half, the entire equation, then that would become 1 half x, half of 4 is 2, and half of 10 is 5. And notice that's the exact same line. Okay. So what we say is that there's an infinite number of solutions, and what we would do is we would solve the equation, and we would say that the solution set, I might be able to solve the equation for x or for y. Let me solve this equation for y. So you'd have 4y equals 10 minus x, y equals 5 halves, so divide by 4, minus 1/4 x. And so what we're going to say is that x is equal to the set of all xy, okay, such that y equals 5 halves minus 1/4 x. Okay, so if there's an infinite number of solutions, what we might do is just solve the equation for y and say it's the set of all ordered pairs that satisfies this relationship. Okay, so now in the next video, we're going to give some names to these. Okay, but I just wanted to go back and remind everybody, because I'm assuming a lot of folks have seen this before, but if not, no big deal. The three possible types of systems. Okay, so there's one solution, no solution, and then an infinite number of solutions. All right, and we can see this by using our graphing method. Okay, so now the graphing method, again, we're not going to use that too often, but it's a good place for us to start with the system. Okay, and if you're ever stuck, you can go ahead and go back to the graphing method to at least get a benchmark as to where the solution might lie. Okay. So in our next video, what we're going to do is we're going to take a look at the different types of systems and what they're called. Okay, so we're going to give specific names to these solutions. And then we're going to go ahead and take a look at various types of methods to be able to solve these systems.